Hello everyone. In our last class we have discussed the Cauchy sequence. So basically first we have discussed the Cauchy criteria, and we say that this Cauchy criteria is your necessary and sufficient, that is if and only if condition, that if your sequence is convergent then it satisfies the Cauchy criteria. So this proof we have done already. Okay, now after that we rename that sequence name if your sequence satisfy the Cauchy criteria, or we can use some two variable m and n. So if it is satisfied this thing, so then we say actually that is Cauchy sequence. So basically here you will see only two defined variable, where earlier it is like n plus p minus this thing, right, xn plus p minus xn. So there is little bit change. Now I already give you the homework. If you read that proof properly, so here you will see that this proof. Okay, so there is actually roll of epsilon by 2, not 3. Okay, so you just check why in whenever this Cauchy sequence is given, why with 2 it is done. So you just observe properly. Okay, and there is another theorem that convergent sequence is always Cauchy. Is a Cauchy. So this proof already we have done. So this is the exactly similar with your this first part, basically from here to here. Okay, so this is same, but here in whenever the first one, that is your yesterday homework, so there you will see up to this part it is okay. Okay, but here there will be roll of 2, not 3, because this type of term is not required there. So you just see this proof is already given in your schema book. You have to take care of that fact. Okay, so this among this proof one may comes in your exam. Okay, so very important. So whenever you are in a real sequence, so Cauchy is equivalent to convergent sequence, that you can say. Whenever your sequence is convergent, you can say that is Cauchy. Whenever it is Cauchy, it is convergent. Okay, so Cauchy if and only if convergent. So this thing also may come. So then you have to write the both homework 3 and homework 4. Okay, basically in the book it is theorem 5.15.2 and 5.15.3. this is according to my book. Maybe if you have different book, so number may be changed. Okay, so this is you have. Okay, now sometimes this type of question is also asked, that so that xn is equal to 1 plus half plus 1/3 dot 1 by n. Problem 1, xn equal to this is not Cauchy. So can you recall this problem where you have seen this? Maybe in your video 2, there you have seen 1 plus half plus 1/3 plus 1/4 using these two terms. Then you have 8 term. So there I have already done. Okay, this type of problem, but there I think instead of this n I have used 2 to the power n notation, right? So in this way you can prove also that if your sequence is not convergent, and you know convergence is equivalent to Cauchy, So in this way also you can prove. And if they ask prove this using Cauchy criteria or directly it is not Cauchy, okay, so there are many types of proof. Okay, so here we can do this thing another way. Okay, so just think here, if I trying to find x m, so x to our m is your 1 plus half plus dot 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 1 by m. So you just think what will be your x to m, 1 plus half plus dot 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 1 by m, then you have 1 by m plus 1 plus 1 by m plus 2 plus dot 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 up to 1 by 2 to the m. Is it correct? So now think, if you consider the product x to m minus xm, so what we will get? Basically this up to this term it will cancel, right? So what is remaining? This term. So you have 1 by m plus 1, 1 by m plus 2 plus dot 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 1 by 2m, right? Now you know m plus 1 will be lesser than 2m, so 1 by 2m will be less than 1 by m plus 1, right? So I can write this is greater than okay, here there is a no role of modulus thing, okay, because you know each term is positive because m is positive, so we can write this is your 1 by 2m plus 1 by, similarly instead of m plus 1 if you write m plus 2 then also it is true, right? So this is also 1 by 2m. So in this way if you write all that thing, so we can write this thing, right? Now you see how many term is there. Basically this is your one term, this is two term, so m plus 2m is, you can think this is like m plus m, right? So 1 2 dot, 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 this is m term. So how many 1 by 2m you are getting? M times, right? So from there you are getting basically 1 by 2m times m, so this is basically half, right? So modulus of x to the power 2m minus xm is greater than half, okay? So you can think you have x, what you have to prove? xm and xn, this is less than epsilon you have to show, right, to prove the Cauchy one. So here you can think instead of m you are choosing 2n. This is just a number, so that term is always greater than half, right? So that is not satisfying. Here you are getting greater than half, where you have to show it is less than epsilon, where epsilon is in your hand, right? Epsilon is arbitrary. So if you choose epsilon is equal to half, so this is not satisfying the Cauchy criteria that there exists no k for which that is happening, right? So if we choose epsilon is equal to half, so then there exists no k for which you can say or you can use your Cauchy criteria definition, xn plus p minus xn less than epsilon for all n greater or equal to k, no k, okay? So it is not Cauchy. Okay, or you can write xm minus xn also, no issue, okay? This is your choice. Okay, next there are some theorem. That theorem name is Cauchy theorem. Okay, so what is this theorem? It's saying if your limit un equal to L, okay, then limit u1 plus u2 plus dot 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 un by n is equal to L actually. Okay, we will prove this. So here basically we will do using two cases. First case is your L is 0. So you know, if your L is 0, so if your un is going to 0, right, that is un is a sequence which is converging to 0. What do you mean by that? So obviously you have, for any epsilon greater than 0, there exists a k belongs to natural number n such that modulus of un will be less than epsilon, right, for all n greater or equal to k, that you can say. Okay, you are writing k1. Okay, fine. Now whenever you have this type, okay, un is also convergent, so un is bounded also, right? Because convergent sequence is bounded, this proof we have done maybe in your second or third classes. Un is convergent, hence bounded. So there exists a b such that modulus of un is less or equal to b for all n belongs to natural number n. Okay, now what you have, u1 plus u2 plus dot 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 un by n less or equal to, so this thing you can break in this way, that u1 plus u2 plus dot 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 u k1 minus 1. So you are breaking that k1 will be inside some function. After that k1 onwards writing other side. So basically you see, you can write this type of number will be less than epsilon whenever n greater equal to k, but whenever it is not, so that you cannot write in terms of epsilon, right? So that's why we break. So this is, but we can write using this b notation for the first this portion. Okay, so you can write this is also b, this is also b. So how many b is there? You can say k1 minus 1 times, right? This is b 1, this is 2, so up to this is k1 minus 1, so k1 minus 1 into b, right? Plus, and this term you can write epsilon how many times? You can say this is n minus k1 plus 1. You just check how many number you are getting. Okay, this is k1, this is your first, k1 plus 1, so this is your 2 term, right? In this way you can take k1 is counting 1, k1 plus 1, this is counting 2. So in this way you can think your final term will be n minus k1, right? In this way you are getting actually n. So this counting will be what? You see, 1 corresponding to 2, right? 0 corresponding to 1. So here this will be corresponding to n minus k1 plus 1, right? So in this way you are getting this. Anyway, this is easy. I think you are now, you can easily count this type of number because sequence we are on the last classes. Okay, so you are having this much epsilon, okay, divided by n, right? Now you can ignore some negative term, no issue, with strictly less than sign. So bk1 by n, and this thing you say n by this time, you can say this is less than if so, okay, sorry, I think here I have to write epsilon by 2, okay. So this is epsilon by 2, because you see n by k1 plus 1, this is less than n, right? So if you divide by that thing, so this is less than 1, so this number is less than 1, so from there you are getting epsilon by 2, okay. Now obviously your job is to find this is less than epsilon, right? Because whenever it is L, you have to prove L. So if it is 0, so you have to prove this limit is also 0. So how to prove this limit 0? So if this is minus 0, this will be less than epsilon, you have to show, right? So this is epsilon by 2 already you got, so you have to show this is also less than epsilon by 2, right? Now you know limit 1 by n is also 0, right? So for any epsilon greater than 0, there exists a number k2 belongs to natural number n such that what you can consider that 1 by n will be less than epsilon by 2 into 1 by bk1 for all n greater equal to k2. Why I am writing? Because our main job is this term should be less than epsilon by 2, right? So you can think we are doing some back calculation that this term if you go there, so that this is less than epsilon by 2, right? This term, okay. So therefore, okay, now you have to choose that thing, right? Choose k equal to max of k1 comma k2 so then you have basically right. So in this way you have to prove this thing. Now you have second case. So whenever you have L not equal to 0 case, we actually try to use the first case, okay. Now your un limit is L, fine, but what you will consider, will consider new sequence Vn, that is un minus L. So if you have this thing, so what is your limit Vn? So this limit is L, so L minus L, so basically 0, right? So from there, using the first case, one, already you have proved that limit n tending to infinity b1 plus, okay, this okay, 1 minute, you just write the final line, thus a limit n tending to infinity u1 plus u2 plus dot dot un by n, this limit is your 0, right? I think this is clear, right? This is sequence if it is 0, so obviously you have to show this thing. Okay, so here you have v1 plus v2 dot 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 vn by n equal to, you have L, 0. Now you just substitute all the value, so So basically this will be v1 will be u1 minus l, right? Second will be u2 minus l dot un minus l by n equal to 0. So this imply how many l is there? You can check. This is u1 plus u2 dot un, you are writing there, then you have minus nl, right? So if you break this thing, obviously you will get that minus l term, and if you write on the other side, this will be your l. Okay, fine. So this is proved. Now there is a similar theorem. If limit un is your L, proof that you can write this in tends to infinity, but sometime they may omit this term. Okay, so then actually it is there, you can think like that. So in root of u1 u2 dot un, this is also L. Okay, this is another thing. So this is actually a coronary of the earlier part. Okay, so what you have to consider, you can think if your un is converging to L, okay, so then your log un converges to log L, right? This is you can write. Okay, so if your log n converging to log L, now you can use your theorem 1, that is the earlier part. So then you can have that log u1 plus log u2, right, dot log un by n. This will be converging to what, or you can say this is will be your log L, right? Now if you use this thing, that logarithm property, so above you have log of u1 u2 dot un, right, and here you have 1 by n. So this 1 by n actually inside the log, this is going to the above part, right, 1 by n. So this is going to log n, right? Now if you log cancel, sorry, this is L, this is L. Now if you cancel that log part both sides, so what you will get in limit n tending to infinity u1 u2 dot un all to the power 1 by n, and this is equal to L. Okay, so this is you write according to you, this part. Okay, okay, now how to how this type of problem may comes in your exam. Okay, for example, suppose they ask find the limit one plus half plus 1 by third plus dot 1 by n divided by n. Okay, this type of problem. So then you have to think, here you have to use the Cauchy theorem. So what is your sequence? xn is your what, 1 by n or un, here un is your 1 by n. Okay, and you know limit un is what, into infinity, this is going to 0, right? So using Cauchy theorem, using Cauchy theorem, what you can say, u1 plus u2 plus dot un by n is equal to 0. So this is nothing but your that thing, that term, so 1 plus half plus dot 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 1 by n divided by n equal to 0, right? Okay. Okay. There is another theorem, that theorem let un greater than 0, that is a sequence of positive number, okay, and suppose they provided limit n tending to infinity un plus 1 by un will be your L. Suppose I am writing L is some finite number, because if it is coming, so there are so many part is there. So suppose you are considering the first finite or infinite, okay. Here we are trying to prove for finite case, infinite is your homework, okay. Then limit n tending to infinity n root of un is also L. So basically if you have the ratio of two consecutive term, that is L, so then you actually get that n root of un is also L. This is very important whenever we'll do the series. There you will see this type of result, okay. Anyway, so how to prove this thing? So consider the case case 1. Suppose 0 less than L less than infinity, that is it is non-zero and non-infinite number, okay. So whenever you have this type of thing, so choose epsilon greater than 0 in such a way, and 0 such that L minus epsilon still greater than 0, that you can choose, right? Because if your L is, suppose it is 0.1 L value, so obviously we can have some epsilon value, so the L minus epsilon will be greater than 1. We will change epsilon maybe 0.05, right? So L minus epsilon will be greater than 0, right? So according to that, if you now break this thing, this sequence, that un plus 1 by un is L, so what you have then, since limit n tending to infinity n plus 1 by un, this is your L. L, right? So there exists K such that L minus, you are writing basically un plus 1 by un minus L, this is less than epsilon by 2, that I can write, right? For all, okay, I am writing K1, that is you can write. So if you break this mod, you can have un plus 1 by un, this is lies between L minus epsilon by 2 and L plus epsilon by 2. Okay. So this is for all n greater equal to okay, this is for not k1, this is for k. It is your choice, no issue, that type of thing you can write. Okay, so if you substitute n equal to k here, so what you have, L minus epsilon by 2 less than uk plus 1 by uk, thus will be this, right? Similarly, right, and you have un by un minus 1 if you do, so you have this type of thing. In the book there is some mistake, okay. No issue. Now if you multiply all the thing, so overall what you see, whenever I multiply this into this, you see this and this cancel, right? So you are getting uk plus 2 by uk, right? So similarly, if you multiply all the thing, you will get un by uk, all that thing. This will be less than L plus epsilon by 2 whole to the power n minus k. Again you collect how many L plus epsilon by 2 on the right hand side. That will be n minus k. You just think yourself. Okay, so this type of thing you are getting. Okay, now your uk, this is some bounded quantity, right? Fixed quantity. So we can say that un will be less than uk times L minus epsilon by 2 whole to the power n minus k. Here also uk into L plus epsilon by 2 whole to the power n minus k for all n greater equal to k. Suppose this quantity is your a, this quantity is your b. Okay, let a is equal to uk into L minus epsilon by 2 whole to the power n minus k, and b is your uk into L plus epsilon by 2 whole to the power n minus k. So you can have a less than un less than b, right? Now if you do a whole to the power 1 by n, so you have this thing. Okay, now your job is to find this limit and this limit. This is basically your sandwich type of thing. What is your a? So here if you do a to the power 1 by n, so this will come here, right? So 1 by that type of thing, right? So overall you will get actually 0, because uk whole to the power 1 by n, this type overall you will get only L, because what you have to show, this is L, right? So now we'll trying to prove this. Okay, so now since you see what is your a term is greater than 0, right? Then limit a to the power 1 by n is always 1. Okay, similarly no, this is not a to the power 1 by n. So a greater than 0, this is fine, but what is your a to the power 1 by n term? So this is basically limit uk whole to the power 1 by n. Okay, then you have l minus epsilon by 2 whole to the power 1 minus k by n, right? Since uk greater than 0, you just write. So uk greater than 0, that means this is going to 1 into, you see k by n going to 0, so you have l minus epsilon by 2. Okay, and similarly limit b to the power 1 by n will be get l plus epsilon by 2. Since your epsilon is arbitrary, right? So, or you can use your direct notation. So thus or since epsilon is arbitrary, so that is actually your L type of thing. So using sandwich, theorem, you can say limit un whole to the power 1 by n is your L. So in this way you can prove the remaining part that are not so much important, but it will help in your concept, because in the series you will see this type of calculation. Okay, obviously in your for the exam this is not so much important. Okay, so this is, you just try at your home. Okay, so this is done. Okay, one more thing. Suppose you have to prove limit n root of n equal to 1. Okay, so this type of thing you can use in your using the previous theorem. Okay, so this is your homework. Fine. Okay, how to prove? Just think your un is your n. Okay, so limit un plus 1 by un, what you are getting, this is 1, right? You just check. So this is equal to limit n tending to infinity n plus 1 by n, so this is, you are getting 1. So if you have this thing 1, so from there you are getting that one, right? Okay, one more thing. Okay, so already we have discussed, right? So this is 1, so this is not your homework problem. So limit n tending to infinity un plus 1 by un will be then 1. Okay, okay, next one is your homework. You practice all the problem. Very, very important, this type of problem. especially this one. Okay. For competitive exam, this result you may note. That lim infimum of un plus 1 by un less or equal to lim infimum of n root of un less or equal to lim sub n root of un less or equal to, or you can write here less or equal to lim un plus 1 by un. Okay, so basically always lim sub is less or equal to lim infimum. This is always happen, but this is a relation where you will see in between lim sub and lim infimum, among these two terms, this is lying. Okay, so basically from here you can say if your un plus 1 by un is exist, so this imply that this limit exists, right? So this is in whenever you will face some competitive exam, this type of result is very, very important. Okay, proof is not important, but for your in exam it is important. Okay, now I will give you a assignment. Okay, so I will send it by tomorrow, today night. So your job will be you have to submit by May 10 or on it when your first class started offline at our college. Okay, so I think let me open the calendar. You know that 4th May is the election result, so maybe if it is started from 7 then it is fine, otherwise it obviously it will start from 11. Okay, so let's see, I don't know the exact date, so according to that date it will be 7 or 11. Okay, so that is the due line. Okay, due date maybe we will see on 11. Okay, fine. So we will start the series, but next few days I will take your senior classes, so you just prepare after this. We will meet at the college with the series 1. Okay, bye.